This video is about logic and reasoning, and its purpose is to help prepare you for proofs in geometry. Now, when we start talking about logic and reasoning, there's really two different types of reasoning. There's inductive reasoning and deductive reasoning. Now, for this class, we're mostly going to be using deductive reasoning. So I really want you to know about inductive reasoning is that you start with the conclusion, or you start with what you observe and you move towards the reason, right? So like, for example, gravity is a great example of inductive reasoning because gravity came about through observation. We observed the way that things interacted, that objects interacted, that planets interacted. And now we have this great system that we can use to describe the very way that motion happens in the universe. That's inductive reasoning. It can be very powerful. The problem with inductive reasoning is that if you have one counterexample, right? If we had one reason that gravity didn't work out, or one way that gravity didn't work out, then the whole system of gravity would fall down, right? So you only need one bad thing to knock it out. And that's why science is always changing, because we find counterexamples. Now, deductive reasoning, and the reason why math is less prone to change than science, I would say, is deductive reasoning starts with a very basic premise. Probably all math, to some degree, starts with the premise of 1 + 1 = 2, or 0 + 1 equals 1, right? But if you can say 1 + 1 = 2, well, then we could say 1 + 1 + 1 = 3, right? As just a next step. And those are airtight, right? Those are solid. So as long as we can agree that 1 + 1 = 2, and I know that there's some snark out there about that not being true, as long as we can agree that that's true, we can form a lot of conclusions from that. And as long as our premises, our basic premises, or premises maybe, are good, as long as the basic place we're starting is good, then all the conclusions we draw from it are good, as long as our logic is sound. So let's look at some logical statements to make sure that we don't run into any fallacies, right? To make sure that we don't run into any errors in our reasoning. So let's look at these few different types of statements. We have conditional statements, converse, inverse, and contrapositive statements. So a conditional statement, and all of these have a hypothesis and a conclusion. And usually we would say the conditional statement is the basis. This is like our starting place. So that P arrow Q is read if P, then Q. And the statement we're starting with this time is, if you are in San Antonio, then you are in Texas. That's true. Okay, so what conclusions can we draw from this statement? Well, what if we flip it around? Flip the hypothesis and the conclusion. If you're in Texas, then you're in San Antonio? No, because I'm in Austin, Texas right now. So I'm in Texas and I'm not in San Antonio. So then that's not true. That's not a good conclusion that we can draw from our original statement. Okay, what about the inverse of that? In that little squiggly line, we read that if not P, then not Q. That's what that little squiggly means, is the inverse or opposite. So the opposite of that, our original statement would be, if you're not in San Antonio, then you're not in Texas. Well, again, you could be not in San Antonio, like Los Angeles, right? In California, you're definitely not in Texas. But I'm in Austin, which is not San Antonio, and I am in Texas. So that statement is false as well. So if those two, we would call those errors, right? You can make either the converse error or the inverse error. Be really careful of that when you're proving things or trying to prove things, because you might have a statement that says, we know if you are in San Antonio, then you are in Texas. But if all you're given is that you're in Texas, you can't conclude that you're in San Antonio, right? Or if all you're given is that you're not in San Antonio, well, you can't say that you're not in Texas, because you could be. So just be aware of these logical errors that we can make in math. Okay, so and the last one is actually a true statement. It's the contrapositive. And it's where we take the converse, so Q then P, and then we take the inverse of the converse. If not Q, then not P. So we had our original statement, if you are in San Antonio, then you are in Texas. And when I say San Antonio, I mean San Antonio, Texas. Okay, I know there's some naysayers out there that might say, but there's a San Antonio somewhere else, not in Texas. Okay, if you're in San Antonio, you're in Texas. The contrapositive would be, if you're not in Texas, then you're not in San Antonio. Which, again, if we're talking about San Antonio, Texas, makes sense, right? No matter where you are in the world, if it's not Texas, well, then it's not San Antonio, because San Antonio is in Texas. So that's a true statement as well, that you can use to, or that you can derive or draw from your original statement, which was, if you're in San Antonio, then you are in Texas. And that's those first statement and the last statement are both true. Converse, inverse are both false. That's what you need to remember. And yeah, we'll do truth tables in the next segment. Okay, so let's talk about one last statement called a biconditional statement. It's an if and only if statement, like a definition. And it's true if both the original if P then Q and if Q then P are true statements. And that's, its notation is a double arrow, or if with two F's, or P if and only if Q. Okay, now here's an example, but it's not really a good one, because you eat cake if and only if it is your birthday. Man, I eat cake all the time, not on my birthday, especially when it's other people's birthdays, right? So I was thinking about this, and let's see. You have the best geometry teacher if and only if you are in Mr. Dussold's class. Okay, so let's take this. Let's see if it's biconditional. Okay, if you have the best geometry teacher, then you are in Mr. Dussold's class. Definitely true. Definitely true. If you are in Mr. Dussold's class, then you have the best geometry teacher. Also true. So that's an example of a biconditional statement. It works both ways. And really, these are mostly used for definitions. Like, if a figure has three sides, then it is a triangle, right? And if a figure is a triangle, then it has three sides. Probably three sides and three angles is a better way of saying that. But, right, those are mostly, biconditional statements are mostly used for definitions. Okay, so that's some basics for logic. Next up, we will talk about, or we'll go through some examples of what that might look like in geometry. See you next time.